Let's now go ahead and draw the shear force diagram. And of course, I invite you to do that yourself. You know already that you need an identifier, and the identifier in this case is the V. So I put the V here, and this also happens to be in Newton. And this would be identical. We have an x-axis that goes to the right, and then a vertical axis that identifies the shear force in Newton, but you will never see this, so I'm going to spare this now. What I will do instead, I will bring in the values from my lecture 13. And the first value that I calculated at x equals to 3.99999 was plus 11.43, if I'm not mistaken. So the way I'm going to do that is I'm going to say that this here is plus 11.43. And this is just a help for me right now. That has nothing to do with the graph yet. I just want to bring over the values. I'm going to bring over the next value, which was plus 1.43. And then I had a value of still plus 1.43, and then I had a value of negative 23.57. So negative 23.57. Now let's think about how we graph this. Let's start with the values that we have, and that should be fairly easy. Remember that positive now is on the opposite to the reference fiber, so I'll just claim that I have a positive 11 point something right here, 11.43. Then I go down to 1.43 and I claim that's here. And therefore I have the same value here on this side. And now I go down to negative 23, and let's pretend that's right there. So far so good. That is probably easy for all of us to do. Now think about what affects these values and the equations that you see in your previous lecture. And what you will find is that because we're dealing with concentrated forces here, this is only concentrated forces, you have no effect of the distance. So what I mean by that is, remember that we cut this system here like this, and that was the value that we received with 11.43 here in the first instance at 3.999. So that is because I cut the system here. If I would have cut the system at, let's say, 2 meters, the value would have come out to be exactly the same. So 11.43, because the equation would have looked exactly the same. So take a deep look at your equation in front of you from lecture 13 and notice that the length of this member did not contribute. And what I mean by that is that now I can go ahead and actually calculate or draw the values. I can draw it here, I can draw it here, I can draw it here. And you will see that once again it's a constant. Now take a look at the equation for the shear force that you prepared for this location here for 4.00001, and then compare it to the equation that you wrote down for 4.99999 at this location. And what you will find is that the length here, the 1 meter, also does not contribute or does not play a role in that particular equation. This will be different later, so be careful with that. But hopefully you see that you could have graphed the value here, 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 and so on and so forth. And now if you understand that, you may believe me that if I make a cut here and here and here and here and here and here, I would find the same value as I would find over there. And so I can graph that, of course, as well. So I can just move in this way. And as I mentioned before, our goal, of course, is not to draw every instant of the value, but rather to act like functions here. So I have a constant here, and then I have a constant right down here as well, and I have one here. And this, of course, is not a full graph yet. Why not? Because I need to do the same thing that I did for my normal graph here. Here I started at 0, and I also ended at 0. And so here I would also start at 0, and the first thing that brings it up is this 11.43, right? So we go up to 11.43 right there. And so the first thing that you can memorize for sure for each of these graphs is that you always start at 0. Okay, and then if I reach the next instance, where I have a jump in the force, I have to, of course, go down, and I do the same thing here. And then, similar to my logic that I used right here, I have to end up at 0 here as well. So I cannot keep this open here, because the value has to go back to 0. And if you don't believe that right now, you will definitely believe that if you have some practice with these problems. But now it's a closed diagram, or a closed shear force diagram, which I complete now by my plus and my plus here and my negative. And I have to indicate this. And students always ask me, is this really necessary? This is just a waste of time to actually shade the area. And no, it's not a waste of time, because these graphs will become more complicated as time goes on. And then you have to clearly identify that you understand where something is positive and where something is negative. And then the way you would see it in the real world would be, you would have here plus 11.43, plus 1.43, and then minus 23.57. And that is now a complete shear force graph, which has an identifier, it has a unit, it has what's called significant values. So these are the significant values, and it has the shaded areas and the positive and negative clearly identified. Now, what is a significant value? A significant value is a value that represents the entire behavior. So from here to here, it's 11.43, then we have a jump, then we have 1.43 is another significant value, and then we have another jump. Let's talk about the jumps real quick. In fact, you might have already seen this. So what is the jump really? So the jump here in this case is what? RAY. And why is it that jump? Because RAY is really what introduces the shear force. Remember what a shear force is? A shear force is a force that is perpendicular to the axis of the beam. In this case, it's in the y direction. So we can understand that every force that acts perpendicular to the beam, like the 10 and the vertical component here, have to have an influence on the shear force diagram. And you see it here, RAY. How big is this jump here? That jump is exactly the force of 10 newtons here on the top, right? So that jump is 10. So this is 10. This is just for education. Nobody would write this later on, right? But I want you to see that we have a jump of 10 here. And then what other jump do we have? We have a jump here that I'm going to copy over to the other side. So we have a jump that is right here. And that jump is actually equal to 50 times sine 30, right? Because that is the vertical component. And then we have a last jump here, which is equal to RBY. All right, so now we understand every element of the shear force diagram, and let me show you the very first shortcut to drawing these diagrams, which you should take with a word of caution, because I don't want you to immediately use them. I first want you to really develop an understanding. But just because it's such a pretty picture here, I can show it to you already. So I started at 0, and it's important to note that the reference fiber is on the bottom and where my arrows point, right? So I have 11.43 here. So I'm jumping up, and then I move to the right. Again, I can move to the right because my reference fiber is on the bottom, because that's the positive x direction. So here's how I do this. Okay, jump 11.43. Nothing happens, nothing happens, nothing happens, nothing happens, nothing happens, nothing happens, nothing happens. Ooh, 10 happens. Okay, I jump down by 10. Nothing happens, nothing happens, nothing happens, nothing happens. Ooh, something happens. What is the jump here? The jump is 50 times sine 30. Nothing happens, nothing happens, nothing happens, nothing happens. Or I should show it here. Nothing happens, nothing happens, nothing happens. And then I bring back to 0 with 23.57. And boom, I have my entire shear force diagram created. Now, don't think that is always that easy. You can always use that logic, but it's not always that easy. What I want you to understand for now, before you see more complicated problems, is that we just follow the arrows and move to the right. And that works actually in all scenarios, but sometimes it becomes a little bit more difficult to implement. However, you have now created your very first shear force diagram.